Okay, thank you very much. And good afternoon to everybody in Warrington, and good afternoon to everybody in Zoomland. So this is dark matter. And for quite a while now, we have realized that the universe has a dark side. For best part of 100 years. So dark matter isn't new in that sense. It's getting on for a century old. And this little cartoon summarizes our lack of understanding. If you can't read what's going on at the bottom there, the professor at the front of the class is saying, after the discovery of antimatter and then dark matter, we have confirmed the existence of doesn't matter, which does not have any influence on the universe whatsoever. So I'm going to try and convince you that dark matter does have an influence on the universe. So if we divide stuff, meaning matter, if we divide it into two categories, stuff we know about and stuff we don't, it's rather embarrassing to admit that the stuff we know about is only 16% of all the matter in existence. That 16%, if we take that to one side just for a moment and subdivide that 16%, we find that most of it is actually just gas. We might think of all the matter in the universe, surely a lot of it must be stars. Well, actually, no. A lot of the matter of the universe is actually just hydrogen and helium, effectively what's left over from the Big Bang. You notice that a small fraction there is actually stars, only 2% out of that 16%. The other 1% I'm not going to talk about, that's just a fundamental particle called neutrinos, which I'll mention towards the end of the talk. But all of the gas and dust and stars of the universe make up this 16% that we know about, but the big question is, well, what's the other stuff then? What is this 84%? And that's what I'm talking about this afternoon. So I'm going to be introducing the basic idea of why dark matter is dark and why that's not a very good word to describe it. I'll be looking at the evidence. I probably won't have time to cover all four strands, but there are three that I will go through, three aspects of evidence that tell us that dark matter exists. I'll be talking about galaxies, stars, and gravitational lensing. I'll probably leave the fourth one, but it is available in a handout if anybody wants to catch up later. I'll be trying to answer the question, well, what is dark matter? What's it actually made of? And there are two possible candidates, which I'll explain when we get to this point, what those acronyms actually stand for, machos and wimps. And I'll finish with, well, does it actually matter? We seem to be in a universe which is dominated by dark matter compared to ordinary matter. Does it actually make any difference whatsoever? That's where I'll finish. Okay, so we can start with, why is it dark? We call it dark matter, and that makes us think that it's something like a dark nebula. It would show up if it was against a bright background. But actually, that's a false way of thinking of what this stuff is. Why is dark matter dark? Well, it's dark because it's not light, but that's a rather facetious way of giving an answer to a question like that. A more useful answer to what is dark matter and why do we call it dark matter is because it doesn't behave the same way as what I would like to call ordinary matter. Ordinary matter is the matter of you and me and the air and the trees and everything on Earth, everything in the solar system that we can see is ordinary matter. A lot of it is made of atoms, not necessarily exclusively, but a lot of it is made of atoms. Dark matter doesn't behave the same way as ordinary matter. Ordinary matter interacts through what we call the electromagnetic force. In other words, the electromagnetic force is the force that's responsible for the attraction between electrically charged particles, attraction or repulsion of electrically charged particles, and ultimately that's why matter either emits or absorbs electromagnetic radiation, which we're just going to call light from now on. It doesn't matter whether we're talking about visible light or infrared or ultraviolet or X-rays or radio, they're all part of the electromagnetic spectrum. Ordinary matter will emit and absorb light, and hence can be detected. We can see stars shining because they emit visible light and we can see them. Some objects might emit radio waves, and hence we can see them with radio telescopes. Other objects might emit infrared light to be seen by the James Webb Space Telescope, for instance. Other objects might emit X-rays. But dark matter does none of this. Dark matter does not emit light, and more importantly, it does not absorb light. We normally think of a dark object as being dark because it absorbs all the light that hits it and doesn't reflect any light. But if that's how dark matter behaved, then we would be able to see dark matter if there was something bright behind it. But no, dark matter doesn't emit light, it doesn't absorb light. A better label would be invisible light, but that's more syllables and not as catchy as dark matter, so we're stuck with the name dark matter. So what we're used to is the fact that everything that we pretty much know up until a few decades ago, or best part of a century ago perhaps, everything we thought we understood about matter was based on the idea of we are made of molecules which are made of atoms, and in some cases the atoms get torn apart, for instance in a big ball of plasma like a star, but ultimately matter is positively charged stuff like the nucleus of an atom and a whole load of negatively charged electrons buzzing around them like bees in a beehive. So that's our sort of picture of what an atom looks like. Strictly speaking, that's not what atoms look like, but we're not going to get into the discussions of quantum mechanics here. We're just going to say that ordinary matter is made of light, and because we've got different charges in the middle and on the outer part of an atom, that can give rise to electromagnetic waves. So atoms can create light, atoms can absorb light. So let's have a start at looking at the evidence that dark matter exists. So this is the first strand of evidence. I'm going to put the numbers up here just so we can keep track of what it is we're dealing with. So the first strand of evidence that dark matter exists is based on observations of galaxies in galaxy clusters. So we can ask the question, what is it that holds galaxies together in a cluster of galaxies? So we can think about, it doesn't really matter which one we choose. In a picture like this, we see a lot of galaxies, possibly tens, possibly hundreds, in some cases thousands or more than thousands of galaxies in a cluster in the same part of the sky, and they all appear to be a coherent object. In other words, these galaxies don't all appear to be in the same field of view by chance. They are genuinely in a part of space, and they seem to be interacting with each other. So what is it that's actually holding those galaxies together? Well, it's gravity. No, it's not a trick question. Gravity is holding stuff together out there. And gravity, as we are all aware, depends on mass. Again, we're not going to get into Einstein's general relativity. We're just going to accept that the amount of gravitational force between two objects depends on how much mass is present. And we can get a reasonable estimate for how much mass we have in a galaxy and a galaxy cluster. It might seem like a rather difficult thing to measure, but you can get a reasonable estimate by looking at a galaxy or a galaxy cluster. You can get an estimate of how much stuff is actually there. You can estimate it from its luminosity. In other words, if you measure the brightness of a galaxy, then assuming you understand how stars work, and let's take it for granted for the moment that we do understand how stars work. We've been looking at stars for centuries within our galaxy. We understand what powers them. We understand how they're born, how they live, how they die. And we understand how they generate their energy through nuclear fusion. So if we understand the processes by which stars give rise to light, then if we look at the brightness of a galaxy, then we have a rough idea of how many stars must be present. Because we know, on average, the brightness of a star. Some are brighter than others, for sure, but when we're talking about billions of stars in a galaxy, we can do a lot of averaging and say, well, on the whole, the average star brightness we expect to be this much, and therefore, if we know the brightness of a galaxy, we can estimate how many stars that galaxy must have. Brighter galaxies must have more stars in them than fainter galaxies, in other words. If we know the number of stars, then we've got a pretty good idea of the mass of all the stars, for the same reason. If we understand how stars are born, how stars live, and how stars die, then by looking at a large population of stars, we know that some stars are more massive than others, but we've got a pretty good idea of what the average is, because we're dealing with such large numbers. So for a given galaxy, we know, roughly speaking, how many stars there must be, and what the total mass of all those stars are. And therefore, we've got an idea of the total mass of the galaxies. We have to take into account the fact that a galaxy is not just the sum of its stars. There's a load of gas in there as well. But I've said here, roughly, we can't get it to 6 decimal places, but we can estimate to within a few percent how many stars, the mass of all the stars in a galaxy, and hence the mass of a galaxy, simply by looking at its brightness. So if we do that for all the galaxies in the cluster, we do that literally for every object in a particular cluster that we can see, every object that appears to be part of a cluster, we can measure its brightness and determine what its mass must be. If we do that for all the galaxies in the cluster, we now have an estimate of the total mass that we're looking at. And remember, the gravity that's holding that galaxy cluster together is the result of the total mass of that cluster. So if we've got an estimate of the mass, we've got an estimate of the gravitational forces holding that cluster together. But even back in the 1930s, this is why I'm saying that this problem is getting on for 100 years old now, even in the 1930s, it was realized that if you calculate the total gravity that's keeping this cluster together, it's not enough to keep the cluster together. Surely these galaxies should have drifted apart by now because the total mass is not enough to provide the gravitational force to hold that many galaxies together. And we've said it's not just a fluke. We don't believe we're looking at a collection of galaxies that just happen to be in the same part of the sky. We don't live in a particularly preferential time to believe that, well, if we looked a little bit later, we would find they would have drifted apart. If it looks like they're all bound together, then presumably the gravity must be strong enough to hold them together. And yet, when we try and work out the mass of the galaxy cluster, it's not enough to hold it together. Something is wrong. So back in the 1930s, this was referred to as the missing mass problem, because there seemed to be some mass that we weren't taking into account by looking at the luminosity of a galaxy. Adding up all the stars doesn't seem to give us the right answer. The missing mass problem. So using luminosity to find mass appears to underestimate, not by a little bit, it doesn't underestimate the mass by 10% or 20% or 30%. It looks like the amount of mass that we actually need to hold a galaxy cluster together could be 4 times bigger, 5 times bigger, 10 times bigger than the actual amount of mass that appears to be there. It's not a trivial little correction. It's not just something in the next decimal place. It looks like there's more missing mass than there is actual mass that we can account for. And here's a sentence that's going to crop up more than once. It would appear. It's as if there is some additional mass that we're not taking into account. It's not luminous. We're not taking it into account by counting stars. This additional mass is providing the extra gravity that's needed to keep the cluster intact and bind the galaxies together. What are we going to call this missing mass? Well, let's call it dark matter. Sounds pretty cool. We've already established that it's actually not the correct name in the sense that dark matter isn't dark, it's actually invisible, which is not the same thing. But unfortunately, the word dark matter has been around for quite a few decades now, and the name has stuck. So we're now stuck with it. So there's a strand of evidence. We've looked at large numbers of galaxy clusters, and every time we try and work out the total mass of the galaxy cluster, it's not enough to hold it together. There must be more mass present. Let's have a look at a second strand of evidence.
So one question.
Mm-hmm.
You say that you need this mass to hold the galaxies together.
Hold the galaxies in the cluster, yes.
Wouldn't gravity hold it together?
No more than the Earth gets pulled into the sun. It's orbiting, so there's motion. As long as you've got motion, you can have gravitational attraction of two objects like the Earth and the sun. The sun is not going to swallow the Earth because the entire solar system is in motion. Same for galaxies in a galaxy cluster. The galaxies will be in motion. So yes, gravity will be trying to pull them in, but the motion of individual galaxies will stop them getting sucked into the central point. Okay? They need the dark matter because if you work out the mass that's there, they should have just drifted away. In much the same way that if you said, well, what if the sun was only 1/10 of the mass it actually is? Well, then we couldn't explain why the Earth is in orbit. Surely the Earth should have flown off ages ago if the sun wasn't the mass that we think it is. If it was only 1/10 of the mass, it wouldn't provide the gravity to keep Earth in orbit. And it's the same argument with the galaxies. They would have flown off, they would have drifted apart long ago. When we work out their velocity and work out the gravity, there is a mismatch. Second strand of evidence, not galaxies in a galaxy cluster, but stars within a galaxy. all galaxies rotate. We're coming back to sort of the previous argument, if you like, of Earth goes round the sun at a particular speed because the sun provides a particular gravitational pull. If we look at stars within a galaxy, then we can ask the question, how fast are the stars moving? In other words, as the galaxy is rotating, how fast are individual stars moving in the galaxy? And we should be able to work out, knowing Newton's laws of motion, or if you prefer, Einstein's general relativity, it doesn't really matter which you choose, you should be able to work out what's the gravitational pull that's holding those stars in the galaxy. We can do that using the Doppler effect. The Doppler effect says that if we have stars moving in a galaxy, at any given instant, some of those stars might be moving towards us, some might be moving away from us as the galaxy rotates. And by looking at the spectrum of stars and looking for particular absorption lines, then we can see that the absorption lines might be shifted towards the red end of the spectrum if the stars are moving away from us, or towards the blue end of the spectrum if the stars are moving towards us. And the amount by which the lines in a spectrum shift depends on how fast that star is moving relative to us. So if we look at lots of stars in a galaxy, we can start to map out how fast those stars are moving. So in the top right here, if we believe this little schematic of a spiral galaxy, a very simplified schematic, if we imagine that there are stars at the center of the galaxy at B, they're not moving, if we assume this galaxy is not receding away from us, this set of stars at B are not moving relative to us, but the stars at A, you can see according to these red arrows here, the stars at A are moving towards us. So any spectrum from a star at position A would be blue shifted because it's moving towards us and would end up with smaller wavelengths because of its motion. Any stars on the right-hand side at C are moving away from us because of the galaxy rotation, and they would have the light from those stars shifted towards the red end of the spectrum. So if we take spectra from as many stars as possible that we can see within a galaxy, and we look at the velocities as a function of how far they are away from the center, we can get an idea of how fast those stars are moving, and hence we can infer how much gravitational force is holding those stars in the positions they're in within a galaxy. Again, on the assumption that we're not seeing this particular galaxy at any special time, we're not seeing it just before these stars go flying off. There must be some gravity keeping those stars moving at whatever velocities we measure. We wouldn't want to choose a galaxy that's face on like this because all of these stars are moving effectively in the plane of the screen that we can see. So virtually none of these stars are actually moving towards us or away from us. So we wouldn't choose a face-on galaxy to do this particular experiment. If we were to look at an edge-on galaxy, then certainly some stars in one part of the galaxy will be moving away from us and some towards us. But of course, we've got this obscuring dust going down the center of this galaxy when seen edge-on. So although this would be a good candidate in terms of the geometry, unfortunately the dust gets in the way when we're looking at a galaxy that's absolutely edge-on. So we'd want something in between. We'd choose a galaxy that's seen at a slightly oblique angle. And some of these stars will be moving towards us and some away from us. It's a little bit tricky to work out which it is because you don't get a three-dimensional picture of a galaxy when you look at this sort of two-dimensional image like this. But we can imagine schematically that some of the stars towards the top of the image, if they're moving towards us, they will be blue shifted, and some of the stars towards the bottom of the image would be red shifted. So I'm not saying the stars will look blue or the stars will look red. It's just an indication of which way would the absorption bands of the spectrum be shifted towards the red end or towards the blue end. So this is just a schematic to remind us that different ends of the galaxy should be giving us different data, different results. And we wouldn't choose necessarily stars very close to the center because they would not be expected to have a significant velocity. But what would you expect to get if you were to map out the velocity as a function of position? What would you expect in terms of orbital velocity? Well, if we ask how should it vary when we go from the center towards the edge, we know what it is in the solar system, for instance. If we were to look at how fast do the planets move on the vertical axis of this graph as a function of how far away from the sun are they, So the horizontal axis here is in astronomical units. So 1 astronomical unit is the Earth, and that has a particular speed around the Sun. And you can see that for Jupiter and Saturn and Uranus and Neptune, the further away from the Sun you go, the slower the objects go. So when all of the gravity is being produced by a central object, and in the solar system, the Sun is essentially 99 point something % of all the mass of the solar system is in the Sun. In other words, the Earth going around the Sun really doesn't care about Mercury and Venus and Mars and Jupiter. It only cares about the Sun that's keeping it in orbit. And this is what we would expect to see if we plot out velocity as a function of distance. We get this characteristic fall off. The more distant objects are further away from the Sun, the pull of the Sun is less strong, and therefore the planets don't move as fast. To a physicist, this makes more sense if you actually plot it on logarithmic scales, and then you get a very nice straight line. But we're not going to worry about that. We're just going to look at velocity as a function of distance, and we expect it to fall off when we are dealing with a situation where most of the thing that's producing the gravity is in the center. So the question is, what do we actually see when we start to plot velocities of stars relative to the center of a galaxy? So we've got a similar type graph here superposed on a picture of the galaxy. And instead of astronomical units, we're now talking about tens of thousands of light years from the center. So the dotted line says, what would you expect? You wouldn't necessarily expect the curve to look quite the same that we had for the solar system, because not all of the mass of the galaxy is in the, usually, black hole at the center of the galaxy. Obviously, there are lots of stars all over the place going out to a particular radius of perhaps 10 to 15,000 light years. If we take that into account, what we would expect by looking at the stars is we would expect the velocities to start tailing off once we get to a position where we're outside that red circle or red ellipse. In other words, what's going on in here is more complicated. If we think of one particular star, it's being pulled inwards by the black hole and other stars, but of course a lot of stars are outside that particular star orbit. So let's not worry about that confusion. Let's ask what's going on if we go beyond 15,000 light years. What happens if we go outside this red circle? It looks like most of the mass of the galaxy is inside that red circle or red ellipse. If we were to simply count stars, then it looks like 99% of the gravity is coming from whatever objects are inside this circle. So once we start going beyond that point, we would expect the velocity to start falling off. Just like when we go from Jupiter to Saturn to Uranus to Neptune, the velocity starts to decline because apparently the gravity should be falling away. Now, it's difficult to find enough stars to measure them when we get beyond this point. So the actual experiments are not done with stars, they're done with gas. In other words, you actually look at the hydrogen and see how fast the hydrogen atoms are moving to judge how much the gravity is falling away. And you would hope that it would start to drop because you would expect it to follow the same law as the solar system. But what you actually find is when you measure the speed of objects, even though you're going further away from the center of the galaxy, they are going faster and faster and faster. It's not falling off. In some cases it flattens off and the velocity is just constant, but in many cases the velocity actually increases the further you go. How can an atom out here be moving so much faster than an atom that's closer to the galaxy? Surely the gravity should be less out there. Surely these objects should be moving slowly, like Pluto, a long way from the Sun. How can we possibly say that these objects are still orbiting the galaxy if they are going so fast? It's the same argument. If these stars and hydrogen atoms are moving at this very high speed compared to what we would expect, it's at least a factor of 2 in this particular case, bigger than we would expect, something is keeping those objects moving faster than we expect. Here's that phrase yet again. It's as if we're missing something. It's as if there's some additional mass that's not luminous, we're not seeing it in the stars, that's providing the extra gravity to keep the stars, or the gas, orbiting at these high velocities, even a long way outside what we would think of as the visible size of the galaxy. Again, we can invoke the existence of dark matter to explain what the stars are doing. So that was a second strand of evidence, independently of the fact that galaxies are held into a cluster. Stars appear to be held in galaxies, and galaxies appear to be rotating much faster than you can account for by the gravity that you can account for in the stars. So what we actually see, in a sense, if you want a cartoon version of what I've just said, if you don't have dark matter, what you would expect, this little video just glitches every few seconds because it resets. The stars are moving quite quickly in the center part of the galaxy because that's where most of the mass is, and the stars around the outer part of the galaxy are moving very slowly, which is what you would expect for something like a solar system. The outer planets move much more slowly than the inner planets. And if you were to look at velocity as a function of distance, it decreases as you go further and further and further away from the center of the galaxy. That's what you would expect. But what you actually see when you look at the rotation of galaxies is that the stars on the outside are moving almost as fast, in some cases faster, than the stars that are relatively close to the center of the galaxy. So you can see the difference here. The outer stars are moving very slowly, and on the right, the outer stars are moving relatively quickly. In other words, if you look at the outer stars compared to the inner stars, the difference is just what's going on. The inner stars are moving at the same speed in these two little cartoons, but the outer stars are moving quite differently. And when we observe galaxies, it's the right-hand picture that seems to be what we see. And we can't account for that unless we invoke the existence of additional matter beyond what we can see from the stars in the galaxy. Strand of evidence number 3, independent of the previous two. We can calculate mass from its gravitational effect, not on galaxies in a cluster or stars in a galaxy, which is strands number 1 and 2, but on light itself. We can calculate mass from the gravitational effect on light. Yes, I know I've said that dark matter doesn't interact with light, for sure. It doesn't generate light, it doesn't absorb light, but if it has mass, then we should be able to see the effect of that mass through its gravitational pull. In other words, it will bend light. Light is bent by gravity, and if dark matter has mass, and it must do to have gravity, then it should bend light. So dark matter should bend light just like ordinary matter does. So by bending light, what I'm talking about is, one way to visualize this is to say that, well, Einstein says that if you have a large enough mass, it will distort space, it will curve space, and light will then follow that curve and produce a sort of lensing effect, if you like. You don't have to worry about matter bending space. All that matters is that matter does interact with light, in the sense that it will make light bend. If we take a distant galaxy, we might think of the light from that distant galaxy following a straight line to Earth, where we observe it in a telescope, for instance. But we know, we've actually observed this many times with Hubble Space Telescope and indeed a lot of ground-based telescopes, we know that if we observe distant galaxies, sometimes we see the light not simply traveling directly to us, but sometimes the light curves or takes a very non-linear path, a rather wiggly path sometimes, to reach from a distant object to the Earth if it happens to travel through a galaxy cluster. A galaxy cluster behaves a bit like a lens, a rather bad lens compared to the sort of lens you might expect in a telescope, for instance. A rather poor quality lens can make the light travel through different paths. And if light travels in different paths to reach the Earth, that means the distant galaxy can be seen effectively in two places at the same time, or at the very least it can seem rather distorted. For instance, a distant galaxy which ought to appear just as a little point of light, as shown by this little inset, can actually be imaged as a rather distorted image depending on the path of light through this galaxy cluster. We're calling it a galaxy cluster just because it has to be large enough to give the effect we're looking for. In principle, any mass can bend the path of light. And here's one example of an image that's taken where a distant galaxy is very distorted such that it ends up looking like a horseshoe. This distant galaxy probably looks like much any other spiral galaxy, but because there's this orange galaxy which happens to be in its line of sight, that's bending the light and producing an extreme distorted view of this distant galaxy, because the light is taking different paths by passing through this region of space occupied by this orangey galaxy, which is more in the foreground compared to the blue galaxy in the distance. If you're finding it difficult to work out how on earth can a lens of some kind give you a horseshoe, well, let me show you a very poor lens. Here we have a distant light source, otherwise known as a candle, and here we have the bottom of a wine glass. The bottom of a wine glass is a very bad lens in the sense that it's not manufactured to be something that produces images. And so when we hold up the bottom of a wine glass and look at a candle, we can get multiple images of the candle. And in some cases, the candle shows up as arcs as well as distorted versions of the candle. Sometimes we end up with two arcs of a candle. And if we hold the wine glass in just the right shape, we might actually end up with an image of the candle which appears to be an entire circle. What we saw before was an almost circle. It was a horseshoe. The circle wasn't quite complete. But you can see that because light takes different paths through the base of a wine glass, we can end up with all sorts of distortions of the more distant object. So if we look at a candle and we see a candle, then we guess that there's not much between us and the candle. But if we look at a candle and we see lots of multiple versions of the same candle, or the candle looks very distorted, or the candle looks like a circle or a horseshoe, we can deduce that there's a lot of mass between us and the distant candle, producing a distortion of the light. So here's an example, another example. The orangey objects, the yellowy orange objects, are galaxies that are, relatively speaking, in the foreground. And some of these more distant galaxies you can see don't look like galaxies, they look like tadpoles or lines or streaks or arcs. The more you look, the more you see. A lot of these more distant galaxies have been distorted from what we would normally think of as normal spiral galaxies into extremely elongated arcs or lines by the presence of the mass that's in that galaxy cluster. It's not easy to do, but the distorted images can tell us about what mass must be present. It's very tricky to do. It's relatively straightforward to say, if I had this mass, how would it affect the light? It's much more difficult to say, if the light looks like this, if I've got an image that looks like that, how do I calculate what mass must have produced those distortions? That's actually quite a tricky thing to do, but it is possible to do it. The distortion in the image does allow us to calculate the mass in the lens. And when that calculation is done, the mass required to produce those distortions is more than we can account for by looking at all the stars in all the galaxies in the cluster which is producing that lens. Here we go again. It's as if there is some additional mass that's not luminous, that's providing the extra gravity that's needed to bend the light and produce the distorted images that we see. And it's not just one distorted image. We now have thousands of images of thousands of clusters looking at more distant objects, and they all seem to indicate that in virtually every case, more mass than we can account for is needed to produce these images. So again, dark matter is required. Okay, I hope you're now convinced that dark matter is out there. I'm going to skip over the fourth strand of evidence. There's a little bit about it in the handout if you're interested. But there's plenty of independent evidence from different sources that says something is going on, some matter appears to exist that we can't account for at the moment. But that doesn't answer the question, yes, but what is it? Something is producing that gravity that's either keeping galaxies together, keeping stars in galaxies, or bending the light from more distant objects. There were two arguments as to what the composition of DM, hereafter dark matter is just DM. What is the possible composition of dark matter? There were two candidates. and they are rather whimsically known as machos and WIMPs. Machos, massive astrophysical compact halo objects. That is actually a backronym in the sense that they came up with the acronym first and then engineered it into a particular phrase. Because the first candidate was, well, maybe there are some particles which we haven't found yet. Maybe there is something out there. We know that atoms are made of electrons and a nucleus of an atom is made of protons and neutrons, and we know what they're made of. Maybe there's something out there which we simply do not understand yet. Another particle which is part of the particle zoo which we haven't accounted for. And it can't interact very strongly. It doesn't absorb light and it doesn't emit light, which is why they're called weakly interacting. Weakly interacting simply means they don't interact through the electromagnetic force. They don't generate light, they don't absorb light. And if they are particles, they must be massive in order to account for this much mass we're looking for. So the idea of WIMPs was around fairly early, but some physicists say, I'm not going to work on WIMPs. That's not the sort of thing I want to admit at a cocktail party that I work on. I'm going to work on machos instead, because they sound much more macho than WIMPs. And then they reverse engineered the massive astrophysical compact halo objects. But the basic idea is this is a new particle we haven't found yet. These are objects we already know about and we are not counting correctly, or something like that. So let me just say what machos are. Again, massive, they've got to be massive in order to produce the effects we're looking for. Astrophysical means nothing other than it gives us an A, otherwise it would be mchos rather than machos. Compact, meaning these are small objects like black holes or neutron stars or something like that. And what do we mean by a halo object? Well, a halo object simply means an object in a galactic halo. Galaxies have a nucleus, they often have a lot of stars. The halo is the large sphere that encompasses the entire galaxy. The halo is the region where, for instance, globular clusters exist. We have perhaps a black hole at the center, we have perhaps hundreds of billions, if not trillions of stars within the galaxy, and the halo is a large sphere which might contain some star clusters, and it is thought might contain these machos. If they exist, they are thought to be normal matter. In other words, we don't have to invent anything new, we just have to make sure we count everything correctly. So maybe these are normal, ordinary matter. They're made of the same sort of atoms as the rest of the universe, but for some reason these objects don't emit any light. If they emitted light, we would have counted them when we counted all the stars. So they must be dark objects. Could they be, for instance, black holes or neutron stars or white dwarfs? Now that might seem a little bit of an oxymoron. How can you describe a white dwarf as an object that emits no light? A white dwarf is a star that's come to the end of its life because it's used all its nuclear fuel, and it starts, once it's generated, it starts as a hot object just because it was the core of a star. If you imagine our sun, if you take the outer atmosphere away, which is what's going to happen when it goes through its red giant phase, what's left is a very hot core. But it's no longer producing nuclear fusion. It's no longer producing energy to keep itself warm. So yes, it starts off very hot, many tens of thousands of Kelvin, but it will just cool off because it's not undergoing any thermonuclear fusion at the core. So a white dwarf will be white when it's born, but it will very quickly cool off, and arguably it will eventually become a black dwarf or something like that. So black holes don't emit light. White dwarfs eventually will cool off to the point where they don't emit much light. So maybe there's lots of bodies like this. They're small enough that we've missed them. They're dark, so they're faint and we've missed them. But maybe that's all we're looking for, is lots of these objects. If it is machos that's the answer to the dark matter problem, how can we possibly detect them? If they're not going to emit light or not emit enough light for us to actually see what's going on, there is another possibility. If they are massive, then they bend light, just like we saw with galactic clusters. It needs to be a slightly different experiment, but it goes something like this. If we are on Earth looking at a distant star, if there are huge numbers of these machos around, if there are huge numbers of black holes or neutron stars or dead white dwarf stars, if they are floating out there and we can't see them, then if we were to look at a distant star, every once in a while, one of these compact objects, like let's just imagine it was a black hole for the sake of argument, one of these black holes might drift into the line of sight between us and a more distant star. And if that were to happen, because this compact object, even if we can't see it, because it generates gravity, because it has mass, it can bend the light from this distant star, it can act like a lens, and temporarily the light we see from the distant star gets a little bit brighter, just because the light is focused a little bit. And then this black hole, which is just drifting through space, minding its own business, that will eventually no longer be in our line of sight, the right-hand panel, in which case the star goes back to its original brightness. So evidence for a macho could be if we look at enough stars continuously and we see some of them rather oddly get a lot brighter. We know what happens if they suddenly get dimmer. That's possibly an exoplanet moving in front of the star. But an explanation of why should a star suddenly get a bit brighter and then go back to its original brightness, that could be the existence of a black hole or neutron star or something else that happens to drift into our line of sight. But of course that's not very likely. So the only way we can really do an experiment like this is to look at not a few stars or a few hundred stars. We really need to look at millions of stars and see how many of them appear to have an object moving in front of our line of sight. So that experiment was done to try and work out whether machos are the answer or not. If we imagine this is our Milky Way, this is seen from the inside, but let's just imagine this is the Milky Way seen from the outside. We're looking at the Milky Way side on, the center of the galaxy is around here somewhere, and at the bottom, on the southern side of the galaxy, are the two clouds, the large and small Magellanic Clouds. If we imagine that we're in the main disk of the galaxy, if we were to look at the stars in the large or the small Magellanic Cloud, if the halo of the galaxy is full of these machos, if the halo is full of black holes and neutron stars and white dwarfs that are floating around out there, if there's enough of them to account for all the dark matter, some of them eventually will drift into our line of sight between us and the large or small Magellanic Clouds. So that experiment was done. Telescopes on Earth stared at the large Magellanic Cloud and made a note of the brightness of the stars, millions of them, over a period of, I can't remember how many years. And they watched for signs of some stars suddenly getting brighter, indicating a black hole had drifted in front of our line of sight. What was the result of that experiment? Yes, they found some stars that did that. So yes, there are objects out there in the halo of our galaxy that are very compact and massive. But there weren't enough of them. If you stare at the Large Magellanic Cloud for a few years, you would expect to get a certain number of black holes drifting in front of stars. And a few of them did, but only a few percent. In other words, even if there are lots of them out there, maybe there are millions of them out there, but there's not enough of them to account for the dark matter that we're looking for. At best, a few percent of dark matter might be black holes that we haven't counted properly. In other words, machos. So it would appear that machos aren't the answer to what dark matter is. So we're back with the alternative. Particles that we haven't found yet, not electrons, not protons, not neutrons, something else is out there that interacts very weakly. It doesn't generate light, it doesn't absorb light, but it does have gravity. These particles are massive, so they do have gravity, and there must be shed loads of them out there in order to account for all the dark matter that exists. So they interact through gravity, but not through electromagnetism. I haven't talked about neutrinos, but neutrinos are similar particles. They are particles that have mass, but they don't interact through electromagnetism. So they are, in a sense, similar to neutrinos. These objects that we are trying to identify might be similar to neutrinos, but neutrinos fly around the universe very fast. These heavier particles would presumably be a lot slower, but we're not too sure. If these particles exist, if WIMPs exist, then presumably they were born in the Big Bang, because it's difficult to explain how they suddenly came into existence after the origin of the universe. So if WIMPs exist now, then presumably they existed at the instant of the Big Bang. And given that every particle that we currently understand has an antiparticle, an electron has an anti-electron, a proton has an antiproton, a mirror image, if you like, the same particle but with the opposite charge, then we think that if dark matter particles did get born in the Big Bang, then we think that there would be the opposite of those as well, anti-dark matter particles. Just like an electron and an anti-electron can annihilate to produce energy, the particles would disappear and energy would be created. How much energy? E equals mc squared tells us how much energy we get for a given mass. Then we think that if dark matter particles exist, then they might well annihilate with anti-dark matter particles. But it doesn't seem to be happening. We don't see any evidence of that happening now. In other words, whenever we look around us, we don't spontaneously see flashes of energy coming from what we can deduce to be dark matter and anti-dark matter particles annihilating. But it's been hypothesized, and this is all hypothesis because we don't know anything about dark matter yet in terms of any facts, but it's hypothesized that, well, if WIMPs exist, is it possible that they would end up collecting where the biggest gravity well is? And where's the biggest gravity well in our neighborhood? The sun is a huge gravity well. There's a large amount of mass there, so maybe the WIMPs would be attracted to that. They don't care about charged particles, they don't care about protons and neutrons, but they might care about the fact that the sun is a large gravitational body. So maybe WIMPs have collected in the sun. In which case, it is thought that maybe a lot of dark matter particles are annihilating in the center of the sun. And it is thought that there is a process by which they might generate neutrinos, and it is possible for us to detect neutrinos. How do we actually go about detecting these rather elusive particles? Sounds a bit odd, but what you do is you take a very large tank of water. And when I say large, you might be able to make out that the people on that little ramp there are 2 meters tall. So you can see this is a huge tank of water. How can you possibly detect subatomic particles with a large tank of water? Well, it's analogous to what happens when an object like a fighter jet moves through the air faster than sound. It flies through the air faster than sound, and in a sense, the air can't get out of the way fast enough, and you end up generating shock waves, and you hear a sonic boom. A sonic boom is the result of the fact that the aircraft is traveling through the air faster than sound can travel through the air, and you get these shock waves. There's an optical equivalent of that. So in the case of sound, we call it a sonic boom, but the optical equivalent of that is called Cherenkov radiation. In other words, if a particle travels through a medium faster than light can travel through that medium, you get the equivalent of an optical shock wave, if you want to think of it that way. That's what you're seeing when you look at a nuclear reactor. It's not a question of Hollywood movie makers think that looks really cool. If that's supposed to be a nuclear reactor, let's color it blue because that looks really nice. No, that is genuinely blue, because in this case, particles are being generated by the radioactive decay of whatever's going on inside this nuclear reactor. Particles are being produced and are traveling through the water. We're looking through a water medium here. The particles are traveling through water faster than light can travel through water. And that gives this optical shock wave, if you like, which happens to be a blue flash. So think of it as a sonic boom equivalent, but in light, it turns out to be blue light. We're not going to go through the details of that. So if I wanted to see a particle moving through this water, what would happen is it would produce the equivalent of a sonic boom. It would produce this Cherenkov radiation. It would produce a blue flash. So if we seal this big water tank and we have photodetectors on the outside and the top and the bottom, then the photodetectors would be looking for a blue flash. And in this particular case, because the blue flash happens to have a sort of a headlight effect and shine in the direction that the particle is traveling, if a very fast particle comes through this water tank, it would produce a blue glow on the detectors, in this case down in the bottom right-hand corner, and these ones wouldn't necessarily see that blue flash. So by recording which particular detectors light up at any particular time, you can work out where did that particle come from, just by working out the geometry of the tank and knowing the time of day, knowing where the sun was in the sky. You can work out whether these particles came from the direction of the sun or came from somewhere else entirely. And just to give you a sense of scale, this is what it's like when you empty the tank. There's lots of photodetectors. Each of these photodetectors is the size of a large football. And if you're having trouble getting the scale here, this is 2 men in a boat. So you can see the overall size of this thing is absolutely huge. Having done a little bit of maintenance and replaced some of these photodetectors, they then refill the entire tank with ultra-pure water, switch off the lights, and then wait for these blue flashes to give you an indication of what high-energy particle has just flashed its way through the tank. So that's what individual photodetectors look like. Effectively, they are specialized detectors that are looking at a particular color. They're looking for blue light that occurs over very short time scales. And it's not limited to working in a water tank. It'll work in any situation where a particle can travel faster than light. In other words, any medium, it won't work in a vacuum because light will always outstrip it. But in a medium such as water, it is possible for the particle to travel faster than light can travel through water, because light traveling through water, because of the refractive index of water, light will only be traveling at a fraction of its light in a vacuum, its speed in a vacuum. So these photomultipliers are not only used to see what's going on in water, there are other experiments. And in this particular case, this one is close to the South Pole. It's called IceCube. And if we think of the ice pack there at the top, this is the laboratory, which is sitting on top of the ice pack there. But that's not where the experiment actually takes place. What we've done is drill into the ice pack, and they've threaded, like a string of pearl, lots of these detectors down from the top of the ice. So in other words, the ice is something like 2.5 kilometers thick at the South Pole, and they've threaded lots of these photodetectors on chains and dropped them down from the surface. Just to give you an idea of scale, that's the Eiffel Tower to the same scale. So in this case, it's particles traveling not through water. Well, it is through water. It's through ice. It's traveling through solid water. The particles really don't care whether they're traveling through liquid water or solid water. So the advantage here is that you can have not just a large tank that's many, many meters in size. Here you can have a cube which is 1 kilometer across, 1 kilometer deep, and 1 kilometer high. So you have an ice cube that is 1 kilometer on a side. So you have 1 billion cubic meters of ice. So you have a much larger detector. And the ice is essentially transparent, so you can do exactly the same as you would do in the water tank. Another thought is that, yes, maybe these particles, if they exist, might tend to collect where there's a big gravity well, like the sun. Well, that's possible. The sun, of course, is very big as far as our solar system is concerned, but our sun is quite puny compared to the entire galaxy. It's thought that maybe we ought to be looking not at the center of the sun, maybe we should be thinking about what's going on in the center of the galaxy, because there is a supermassive black hole there with a mass of some 4 million times the mass of our sun, and maybe dark matter particles will start to collect inside black holes, or at least close to black holes. And maybe dark matter annihilation could produce some very energetic gamma rays, it is thought. And so, again, there are experiments to look for these. Again, it's rather hypothetical, but if you don't do experiments to look for these things, you could obviously miss them. So again, coming back to the basic idea, if we think about Milky Way galaxy, the center of our galaxy is roughly in the center of this image. And as you appreciate, if you've ever tried to take a picture of the Milky Way from the UK, the center of the galaxy is relatively low down on a horizon. If you want to see things that are coming from the center of the galaxy, you wouldn't put an experiment in the middle of England to do this. You would do it from somewhere in the southern hemisphere where the center of the galaxy is much higher in the sky. So hence there are plans to produce a so-called Cherenkov telescope array. And they are not looking directly for anything that's coming from the center of the galaxy. What they're looking for are particles that are traveling through the Earth's atmosphere. In much the same way that if a particle travels through water or travels through ice and travels faster through the medium than light can travel, you get a Cherenkov blue glow. The same idea here. The telescopes are not necessarily pointing to the center of the galaxy. They're looking at the sky, which again, instead of just a kilometer in size, you're looking at an atmosphere which is many kilometers in size. So effectively, the size of your detector is now absolutely vast. If there are very energetic particles, which may or may not be coming from the center of the galaxy, as they come through the Earth's atmosphere, if they're traveling faster than light can travel through the atmosphere, they produce a Cherenkov blue flash. And that effectively will be picked up by some, but not necessarily all, of the telescopes. By looking, if you've got a large array of these telescopes, you monitor what each of these telescopes see, and by looking at these telescopes saw a flash, these telescopes didn't see a flash, you can work out where must this object have come from, where in the sky must it have come from, in order to produce this particular pattern of pickup on particular telescopes in the array. So that is effectively under construction. So there are big experiments to look for the possibility of dark matter particles. The Super Kamiokande, the large water tank, I didn't express that explicitly, but that's in Japan. We have the ice cube at the South Pole. We have things like the Cherenkov telescopes. They're situated in the Atacama Desert. All over the planet, there are various big experiments going on to try and understand what dark matter particles might exist. And it's also possible to do smaller experiments, effectively desktop-type experiments. So here's a whole list of them. You can see that they are much smaller by comparison. We're not talking about objects that are kilometers in size. Some of these experiments might be literally desktop and might be the sort of experiments you can do in less than a meter. The idea being, if a very energetic dark matter particle goes shooting through this particular experimental setup, is there something we can do to make it visible? Maybe if this dark matter particle actually hits an atom, is it possible to see that atom recoil like in a game of billiards? If a dark matter particle has enough energy and actually physically hits another object, is it possible to see an atom jump because of impact from a dark matter particle? There are lots of ways it could be done, and here's a few of the acronyms. I won't go through them, but if you're interested, you can go and look up these acronyms. I think the winner probably has to be Edelweiss in terms of actually coming up with an acronym which actually means something, but also gives you a way of identifying particular dark matter experiments. These have been running for quite a few years. Some of them are still being built. Some of them are operational. Some of them have produced some very interesting events. In other words, they've seen things which maybe they can't quite understand, but in many cases the data is either contradictory or at the very least not yet confirmed. So these experiments have been running for years, but we still have not definitively found this particle seen in this experiment is quite definitely a particle of dark matter which we've never seen anywhere else in the universe before. So all of these experiments are ongoing. Before I finish, let me just admit that there are alternatives. I've said that dark matter is out there because we have lots of strands of evidence that say otherwise we can't explain how galaxy clusters hold together. We can't explain how stars go around galaxies so fast. We can't explain gravitational lensing. Well, some people claim, yes, you can. Maybe we've just misunderstood how gravity works. It's not a question of we're missing mass. What we're missing is an understanding of how mass produces gravity and how gravity works. So maybe gravity isn't quite as universal as Newton would have us believe when he developed his law of universal gravitation. Hence, we only seem to need dark matter because we've got gravity wrong. If you admit that gravity is wrong, then all bets are off. So maybe gravity works differently on different scales. Maybe gravity isn't so indiscriminate. We assume, or have done for quite a few centuries, that the gravity that is pulling this laser pointer down to the Earth is the same gravity that's keeping the moon in orbit. It's the same gravity that's keeping the Earth in orbit around the sun. It's the same gravity that's keeping the sun in orbit around the Milky Way. It's the same gravity that's pulling the Milky Way and the Andromeda galaxy together for a collision in a few billion years' time. It's the same gravity that's keeping all of these galaxy clusters together. In other words, gravity is the same regardless of whether you're working on scales of millimeters or whether you're working on scales of millions of light years. But maybe it isn't. Maybe gravity works differently if you look at the scale of the universe or the scale of a galaxy or the scale of a solar system or the scale of the Earth or the scale of a lab experiment pulling two objects together. If gravity works differently depending on what it is you're measuring, then you can get away with basically not requiring dark matter. In other words, you can re-engineer gravity to get rid of the need for dark matter. But in doing that, you're going to have a lot of other problems. So this idea of Newton was wrong, it's not universal, is called modified Newtonian dynamics, or MOND. But so far, anybody who's ever tried to modify Newtonian dynamics such that you no longer need dark matter, it does get rid of that problem, but it introduces 17 other problems. In other words, it's not what we would call a good scientific theory if you've solved one problem but generated a shed load more problems. And no one has yet successfully said maybe gravity works differently on different scales, hence we don't need dark matter, and everything is completely self-consistent. Yay, got it. So the final point is, does it matter? Does it really matter if there is lots of stuff out there that we didn't already know about? Well, it's rather embarrassing to say that we actually only understand 4 or 5% of the universe, and the rest of it is dark matter or dark energy. In this case, the dark matter is the thing we're worrying about. The fact that there's more dark matter than ordinary matter seems to be a little bit perplexing, but does it actually make a lot of difference? What are the consequences if we say, well, let's imagine that dark matter didn't actually exist? Does it just mean that galaxies rotate at a different speed? You know, who cares, basically? Well, whenever simulations are done, you can simulate how we go from the Big Bang to where we are now, 13.8 billion years later. We can simulate that by starting with a whole load of matter and saying, how does that matter behave? How does gravity pull this matter together? How do we end up with galaxies and stars, starting with the Big Bang? And we end up with galaxy distributions that do look very similar to the galaxy distributions that we actually see, but only if we add dark matter into the mix. If you start with a universe that doesn't have any dark matter, none of the simulations that have run in the last few decades can produce a universe which looks like the one we live in. In other words, dark matter is necessary to make the universe collapse the way it appears to have done. Collapse meaning take a large amount of matter and have it collapse into galaxies and galaxy clusters. Let's actually show that in a simulation. If we start with the universe was the size of a golf ball or so, so back in the very early universe, everything that we now see in the observable universe used to be a lot closer together, only a few centimeters or so apart. And there were small variations in the density of the universe, represented by the dimples on the golf ball. If we run a simulation saying, what does that look like if we take a universe which is tiny and then allow gravitation to do its stuff? In other words, if we run a simulation over billions of years, we find that the initial distribution of matter, which we assume was relatively uniform, just small variations in density, if we allow gravity to grab hold of that and run the simulation forward a few billion years, we end up with a universe which is full of filaments and voids and a web structure. And where these filaments cross each other, you get these little concentrations of matter, and that is where galaxies and galaxy clusters form. And when we look out into the universe, we don't see galaxies uniformly distributed over the entire universe. We see them clustered, and we see filaments, and we see voids. In other words, this structure is pretty much what we actually see when we observe the universe. But we can only get that result in 13.8 billion years if the universe is made of more dark matter than ordinary matter of electrons and protons and neutrons, etc. If we leave dark matter out of the mix, we do not end with stars and galaxies, and basically the bottom line is we would not be here, because 13.8 billion years would not have been long enough to make the stars, to make the heavy elements by having lots of stars generate the carbon, the nitrogen, the oxygen, the everything else. So as far as we can tell, life wouldn't exist if it wasn't for dark matter allowing the universe to come together in the way it has over the last 13.8 billion years. So on a large scale, we see the universe as this sort of foamy structure, this cosmic web. And if we look in details, we see, yes, we can see individual galaxies and galaxy clusters, and various astrophysicists and computer specialists are running these simulations to try and understand exactly how the dark matter produced the structures that we ultimately see. It is thought that dark matter produced this cosmic web, and then ordinary matter piled in on top of it. In other words, dark matter actually formed structures first, and then ordinary matter, the stuff that you and me are made of, that piled in on top of the dark matter and produced the galaxies, and then we saw the stars shining, etc., because ordinary matter can emit light, whereas the dark matter can't. So I've given you an introduction to the fact that dark matter is not really dark, it's really invisible, and it's the interaction of matter with light that determines the definition of dark matter. I've shown you 3 out of the 4 strands of evidence, each of which would be good enough to say we need dark matter. All 4 together convinces us that there's definitely something out there that we're missing. What is it that we're missing? Well, it could be a particle we haven't found yet, WIMP. It could be machos. It could be large, massive, compact halo objects. It doesn't look like it's machos. We seem to have nailed that one. There doesn't seem to be enough evidence that machos are the answer. So presumably it's WIMPs. It's presumably some particle that we simply have not seen yet. Despite many hundreds of years of looking, we've somehow overlooked the fact that the universe is not just made of electrons and protons and neutrons and neutrinos. There's another particle in the periodic table, if you like, of fundamental particles, and we've simply missed it. So frantically, people are looking. And does it matter? Absolutely it matters, because it looks like without dark matter, the universe could not have ended up looking like the way it does at the moment. So it started off as an embarrassment in the sense that there appears to be more dark matter than ordinary matter when the observations were first made, but now it seems to look like it is an absolutely essential ingredient of the universe, because without it, we would not be here. Thank you for listening.